This video shows you how to filter unobserved states of a linear Gaussian state space system. My explanations assume that you have looked one of my more intuition-related videos on the Kalman filter, mainly because I rely here on the same notation, and I will focus here more on the algorithm and not so much on the intuition. So let's start. A time-invariant linear Gaussian state space system takes the following form, having a measurement equation and a state equation. So let's turn to the measurement equation. We assume that in point time t we have p measurements. So yt conditional on ft-1 is a linear function in our unobserved state alpha t plus a measurement error epsilon t. So epsilon t conditional on ft-1 information is Gaussian with a mean of 0 and a variance of h. Note we have m states as we have p measurements. Capital B needs to be p times m, and the constant a is p times 1. Now let's turn to the state equation. It's assumed that alpha t conditional on ft-1 is simply a vector order regressive system of order 1, meaning it's the constant c plus capital phi times alpha t-1 plus eta t, and eta t conditional on ft-1 is a Gaussian shock with mean 0 and variance q. Now I get it. Even at the second look, my conditioning on the ft-1 information set might look weird. Yet hang on for a minute here. I argue it's useful because of the following thought. Using the conditioning allows us later on to say that the constant matrices capital B, capital H, capital Q, and capital Phi, as well as the vectors A and C, could be time varying as long as their realized time t-1 values are observed at time t-1. And because of that, we can treat these matrices and vectors as constants. But note, technical textbooks have a time index on these matrices and vectors. But then they say that these are ft-1 measurable quantities. Yet I don't find that to be student-friendly, as there are so many time indices running around. Hence I've decided to use my above notation for this video here. But if you want the most general treatment, then I advise you read the instructive Kalman filter Bible of Durbin and Koopman. So going back to the linear Gaussian state space system, you basically see that the unobserved states follow a vector order regressive system of order 1. You also see that the measurements are a linear mapping of the unobserved state plus additive noise. Now the recursive routine for the Kalman filter reads as follows. Note here, I also use a slightly different notation than what textbooks usually use, but I feel it fits better to my previous explanations if I'm also more explicit for some of the variables. But anyway, let's get to the recursive routine for the Kalman filter. Now first, you initialize the Kalman filter with expert knowledge. Remember, if you feel intimidated by the word expert, Simply use a large variance around your initial guess for the value of alpha 1. That way, your initial guess won't matter that much. Now, let's highlight that explicitly. You need to initialize the first prior. Now, doing so means you have to initialize the conditional expected value of alpha 1 as of f0 and the conditional variance of alpha 1 as of f0. Now, once you have done that, you run through the training set. So assuming you have in your training sets measurements for t being element 1, 2 up to capital T, the loop that you're running through now reads as follows. For t being equal to 1 up to capital T, you determine the following. First, the learning rate, here kt, which is given by the following long expression. Now second, you determine the prediction error, νt, defined as follows. Now in the third step, you compute your posterior estimate. Given that we assume that alpha follows a Gaussian variable, the posterior estimate needs to pin down the conditional mean and the conditional variance for alpha t. So the conditional expected value of alpha t conditional on ft is simply the expectation of alpha t conditional on ft minus 1 plus your optimal learning rate in t times the prediction error at time t. And the conditional variance of alpha t conditional on ft is simply the conditional variance of alpha t as of t minus 1 times the identity matrix minus kt times b. And last, you now determine the prior for the next period. Again, since alpha is assumed to be Gaussian, you need to specify the conditional mean for the next period and the conditional variance. So the expectation of alpha t plus 1 conditional on ft just follows from your drift of the state equation. So it will be c plus phi times the expectation of alpha t conditional on ft. And the conditional variance of alpha t plus 1 conditional on ft also follows directly from the state equation. So it's phi times the conditional variance of alpha t as of ft times phi prime or transpose and then plus system noise q. Now note the following points here. First, with regard to the optimal learning rate kt. Now the expression for kt picks up the expected covariance between the unobserved state alpha t and the measurement yt, normalized by the variance of yt. Now that key quantity figures out how much can be learned from the measurement yt in terms of the realized yet unobserved value for alpha t. Now second, with regard to the prediction error νt. So the linear measurement equation implies that the following relationship holds. Now, my third observation, here with regard to the posterior. The posterior adjusts the prior forecast by whatever yt can teach us about the alpha t. If it cannot teach us anything, we don't update the posterior. If we can learn a lot, we update a lot. And now fourth, the last equation of the Kalman recursion computes the current prior for the upcoming time period. Yeah, and so you see how you really recursively move through your training set. Now, importantly, if you have difficulties understanding that last algorithm, please revisit all the Kalman videos that I have posted. Now, if the difficulty persists, please get in touch so we can talk about that during a tutorial.